We'll finish up this section here looking at the natural exponential function f of x equals e to the x. And I know what a lot of you are thinking. What the hell is natural about the transcendental number e? It works for interest. Why is it anything special? Who do mathematicians think they are calling that thing natural? There's nothing particularly normal looking about it. And in terms of behaviors, it doesn't tend to behave very nicely, at least as far as plugging in numbers goes, because you don't like raising transcendental things to powers. It's not easy. It's not natural. And that's fine. That's fair. That's completely understandable. That's the way I felt about it when I first saw this thing called the natural exponential as well. It seems kind of silly. It seems kind of weird. But you should understand here that for most of history, and still today when we talk about theoretical things in terms of math, the more pure side of math is really closer to philosophy than it is to a science. It's more about behaviors in an abstract sense than the specific applications, even though the natural exponential e to the x does give itself to a lot of really nice, really important abstractions and applications. We should know here that when people call this thing natural, it's not necessarily because it's easy to work with. It's not necessarily because it's obviously important. It's because it is a thing that happens to describe a lot of really important things, and for that matter, has a lot of really important behaviors. And math being more philosophy than science, it does happen sometimes with philosophical texts, with philosophical ideas that, because of the years and years of work that go into them and all the thought that came together with how they define the terms they have, it seems very natural to them, and it makes complete sense to people who follow in their works very closely. But when it comes to us, the people who are inheriting it years later outside of that special context, it just looks like a bunch of weird squiggles that we're claiming are very important. But be patient here. This isn't something that we have all of the stuff for just yet, but if you go further with math, you're going to see that the importance of the number e and the importance of the function e raised to the power x is unavoidable. It's going to be coming back if you go further than this class. But for us, the main thing we're going to look at for why we might call this thing natural is because, thinking back to our language from the beginning of this section, if we want to describe a thing in terms of a constant, consistent, multiplicative growth rate over time, that value e happens to be a really good candidate for a lot of cases, for a surprising amount of things. And we'll finish here with an example showing one way that it can be used. For this, we have that the exponential function f of x equals 1,145 times e raised to the 0.0325x models the gray wolf population of the Great Lakes, the Western Great Lakes specifically, X years after 1978. According to the model, what was the gray wolf population rounded to the nearest whole number of the Western Great Lakes in the year 2021? So, because the year 2021 is 43 years after 78, that makes t equal to 43. And so with our function, we're just getting f of 43, which would be equal to 1,145 times e raised to the power 0.0325 to the 43, where again, this describes a growth rate over time, except that value e is something very special in here that we're going to come back to later in the context of exponential growth and decay. But just know that this guy is really good for that sort of thing. It's really, well, natural. But this will give us an approximate squiggly value of 4,628 wolves, where if you look at more modern estimates, you'll see that they estimate the population to be about 4,000, something a little above, maybe a little below. So it's not the worst model in the world that we have here. Things like wolves are a little bit hard to get a fixed estimate on just because of how much they range and how they tend to be in small groups, so you can't get a perfect matching there for where all of them are, but hey, it's a decent model. Anyway, outside of the realm of applied models, the other big thing that we talked about with these exponentials, or at least one of the big things we talked about with them, is that they're one-to-one. And because they're one-to-one, they have to have an inverse. And then we have to ask ourselves, what would the inverse of something like this look like? And that's what the subject of 4.2 is, with a very special family of functions designed not specifically for that context, but used in modern math for that sort of thing, called logarithmic functions. And that's where we're going next.